In this lesson, we're going to look at one mathematical model that we can use to describe the force of gravity, particularly if we're dealing with objects that are not close to the Earth's surface. If we have an object that's close to the Earth's surface, we can easily calculate the weight of the object by taking the mass of the object and multiplying by the acceleration of gravity, 9.8 meters per second squared. But if we start to move away from the Earth's surface, the gravitational force decreases. And in fact, it decreases as the square of your distance increases. So the force of gravity is related to the square of the distance between the two objects when you start to look at how large that force is. It's also related to the two masses of the two objects. So Newton's law of gravity really says is that the force due to gravity is equal to the product of the masses of the objects, so mass 1 times mass 2, divide by the distance between the two objects squared. If we're talking about large objects like the Earth or the Moon, we might make that distance, how far are you from the center of that object, or the center of gravity of that object. So for the Earth, if we wanted to calculate this for the Earth, I would make r the radius of the Earth in this case, if I was standing on the Earth's surface. The last part of this equation is that there's a constant in here that we use, capital G. This is called the universal constant of gravitation. This is really one way of describing how gravity interacts in the universe. So we know how large this constant is. It's 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. You might say that seems like a really small number, and it is a really small number, and that's because gravity, in terms of kind of the fundamental forces we know exist, is actually the weakest of the fundamental forces. Some things to point out that are kind of interesting about this equation. The first one is that gravity acts between all massive objects and other massive objects. So if you have two massive objects close together, they experience a gravitational force between them. This also suggests that gravity is always an attractive force. That's really what the negative sign of this equation is saying, is that the force always attracts massive objects to other massive objects. Idea of weightlessness. And weightlessness is kind of an odd thing in that we can actually experience a sensation where you don't feel like you have any force of gravity acting on you. If we take you up to the International Space Station, or really any other object that orbits around the Earth, you experience the feeling of weightlessness. Now, does this mean the force of gravity from the Earth acting on you is zero? The answer to that is no. Earth is still applying a gravitational force on you. In fact, when you get to a distance as far as the International Space Station, the force due to gravity really hasn't changed all that much. So what is going on that allows you to experience weightlessness? So your first inclination might be, well, gravity must not be very strong at the International Space Station. That's why I don't feel it. But if we actually do the calculation where the International Space Station is, what you find is, no, that's not really the case. So what I've done here is I've plugged in my mass, 65 kilograms, the mass of the Earth, 5.97 times 10 to the 24th kilograms. How far the International Space Station is above the Earth's surface, 4.01 times 10 to the 5th meters, and added the radius of the Earth, 6.37 times 10 to the 6th meters, and squared that. And I get the force due to gravity if I'm in the International Space Station. Earth is applying a force of 565 newtons on me. If I calculate what the force due to gravity that I experience here on the Earth's surface is, well, it's 637 newtons. Well, that didn't change all that much. That's maybe a decrease of 15%. So this must not be that the gravity is not very strong at the International Space Station. There must be something else happening that causes me to feel weightless. So what's going on here? Why do I feel weightless if I'm on the International Space Station? So what's going on here at the International Space Station is you are on an object that's orbiting around the Earth's surface. You're actually falling around the Earth. We're using the Earth's gravity to keep you in this orbit. So you're technically in free fall around the Earth as you orbit around the Earth. You're just moving fast enough in a forward direction to continue to move around the Earth in a circle. We'll get to this in a little bit when we talk about circular motion and circular orbits, how that actually works, because there is a particular speed that you need to be traveling at the location of the International Space Station to stay in orbit around the Earth at that distance away from the Earth. So what's happening is you've no force supporting you, so you really have no normal force acting on you since you're in free fall. Well, remember what we said, that your perception of how heavy you are when we did the elevator problem is really how big the normal force is that's applied on you. Well, if you've no normal force applied to you because you are falling at the acceleration of gravity, then you're going to perceive your weight to be zero, or you're going to perceive yourself to be weightless. So this is more of how your body perceives weight more than is gravity actually acting on you. In the orbit around the Earth, yes, the gravity here still acts on you. In fact, it hasn't really changed all that much going up to the International Space Station. What's happening is you're moving in this circular orbit around the Earth, which causes you to experience weightlessness. So that's Newton's law of gravity, and one way we can use it. We can also use that as a way to describe how big the force between planets is, or how big the force between the Earth and the Moon is. We don't usually use it to talk about massive objects kind of in the classroom because those forces are usually really, really small. We'll start to do in kind of the next set of lessons is start to look at circular motion a little bit.